Subscribe so you don't miss out on any of these videos. Space, the final frontier, has captivated humanity's imagination for centuries. It is an infinite expanse, filled with wonders and mysteries that go beyond our wildest comprehension. Every discovery we make about space only adds more questions, revealing how little we truly know about the cosmos. The vastness of space is mind-boggling, and the facts we've learned about it are enough to make anyone pause in awe. From the smallest particles to the largest celestial bodies, space holds some of the most mind-blowing phenomena in existence. Let's dive into some of the most astonishing facts about space that challenge our understanding of reality. Space is big. Really big. The human brain is not equipped to fully comprehend just how vast the universe is. For example, the observable universe is about 93 billion light-years in diameter. That means if you could travel at the speed of light, it would take you 93 billion years to cross from one end to the other. But that's only the part of the universe we can observe. The actual universe could be much larger, possibly infinite. To put it in perspective, if you were to shrink the Earth to the size of a grain of sand, the observable universe would still be over 60 trillion times larger than that. One of the most astonishing facts about space is that we are constantly moving, even though we don't feel it. Earth spins on its axis at about 1,000 miles per hour. At the same time, it orbits the Sun at a speed of around 67,000 miles per hour. Our solar system, in turn, orbits the center of the Milky Way galaxy at a staggering 490,000 miles per hour. Even our galaxy is moving through space at a speed of 1.3 million miles per hour. Despite all this motion, we feel still because everything around us is moving at the same speed. Another mind-blowing fact about space is that it's not empty. We often think of space as a vacuum, devoid of matter. While space is indeed much less dense than Earth's atmosphere, it's not entirely empty. It contains gas, dust, and tiny particles, as well as dark matter and dark energy. In fact, dark matter and dark energy make up about 95% of the universe's total mass and energy. Despite its abundance, dark matter cannot be seen or touched. It interacts only through gravity. Scientists are still unsure what dark matter is, but it plays a critical role in holding galaxies together. Black holes are one of the most mysterious and fascinating objects in space. These are regions of space where the gravitational pull is so strong that nothing, not even light, can escape. Black holes are formed when massive stars collapse under their own gravity at the end of their life cycle. The boundary around a black hole, called the event horizon, is the point beyond which nothing can escape. Inside the black hole, the laws of physics as we understand them break down. Time and space become warped, and the singularity at the center of the black hole is a point of infinite density. Perhaps one of the strangest aspects of black holes is their effect on time. According to Einstein's theory of general relativity, time moves more slowly in stronger gravitational fields. This means that if you were to approach a black hole, time would slow down relative to an observer farther away. In fact, if you could survive getting close to a black hole, which is impossible due to the extreme gravitational forces, you would witness the universe outside speeding up while you seem to stand still. Time dilation near a black hole could theoretically allow for time travel to the future, although it's not feasible with our current technology. Another astonishing fact about space is that it's expanding. The universe has been expanding ever since the Big Bang, about 13.8 billion years ago. This expansion is accelerating due to the influence of dark energy, a mysterious force that makes up about 70% of the universe's energy. As space expands, galaxies move farther apart. This means that over billions of years, galaxies will drift so far apart that they will become isolated, making the universe a much lonelier place. Eventually, distant galaxies will move beyond the observable universe, disappearing from view forever. Speaking of the Big Bang, this cosmic event marks the beginning of space and time as we know it. Before the Big Bang, the universe was in an extremely hot, dense state. In an instant, it expanded rapidly, creating all the matter and energy that now exist in the universe. The remnants of the Big Bang can still be detected today in the form of cosmic microwave background radiation, a faint glow that permeates the entire universe. This radiation provides valuable information about the early universe, helping scientists understand how galaxies, stars, and planets formed. Stars are another wonder of space that never cease to amaze. Our Sun, for example, is a massive ball of hydrogen and helium undergoing nuclear fusion in its core, producing light and heat. But our Sun is just one of billions of stars in the Milky Way galaxy, and it's not even a particularly large or bright one. In fact, there are stars out there that make the Sun look like a tiny speck in comparison. For example, the star Uy-Scuti is about 1,700 times larger than the Sun. If you placed Uy-Scuti in the center of our solar system, its outer edge would reach beyond the orbit of Jupiter. Stars also have life cycles, and their fates depend on their mass. Smaller stars, like the Sun, will eventually expand into red giants before shedding their outer layers and leaving behind a dense core known as a white dwarf. Larger stars, on the other hand, will explode in a supernova, an incredibly powerful explosion that can outshine entire galaxies for a brief period. These explosions create heavy elements, such as iron and gold, which are then scattered throughout the universe, eventually becoming part of new stars, planets, and even living organisms. The process of star formation is equally fascinating. Stars are born in vast clouds of gas and dust known as nebulae. As gravity pulls the gas and dust together, the material forms a dense core that eventually becomes hot enough to ignite nuclear fusion, giving birth to a new star. Some nebulae, like the famous pillars of creation in the Eagle Nebula, are stunningly beautiful, with towering columns of gas and dust illuminated by the light of nearby stars. One of the most intriguing aspects of space is the possibility of life beyond Earth. With billions of stars in the Milky Way alone, and each star potentially having planets orbiting it, the chances of life existing elsewhere in the universe seem high. Scientists have already discovered thousands of exoplanets, some of which are located in the habitable zone, where conditions might be right for liquid water and life to exist. However, we have yet to find definitive proof of extraterrestrial life. The search continues, with missions like the James Webb Space Telescope and future space probes aimed at exploring distant planets and moons for signs of life. One of the most promising candidates for life in our solar system is Europa, one of Jupiter's moons. Beneath its icy surface lies a vast ocean of liquid water, kept warm by tidal forces generated by Jupiter's immense gravity. Scientists believe that this ocean could harbor microbial life, similar to the organisms found in Earth's deep-sea hydrothermal vents. Future missions to Europa aim to drill through the ice and explore the ocean for signs of life, potentially answering one of humanity's biggest questions: are we alone in the universe? Another fascinating moon in our solar system is Titan, one of Saturn's moons. Titan has a thick atmosphere made mostly of nitrogen, and its surface features lakes and rivers of liquid methane and ethane. While the conditions on Titan are vastly different from those on Earth, some scientists speculate that life could exist in its methane lakes. Titan's atmosphere and surface chemistry also bear some similarities to early Earth, making it a valuable target for future exploration. Space is also home to some of the most extreme environments imaginable. For example, the surface of Venus is hot enough to melt lead, with temperatures reaching up to 900 degrees Fahrenheit. Its thick atmosphere, composed mostly of carbon dioxide, creates a runaway greenhouse effect, trapping heat and making Venus the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. In contrast, the coldest known place in the universe is the Boomerang Nebula, located about 5,000 light-years from Earth. The temperature there is just 1 degree Kelvin above absolute zero, which is the lowest possible temperature, where atomic motion nearly comes to a halt. Even the vacuum of space, which averages about 2.7 Kelvin due to the cosmic microwave background radiation, is warmer than this frigid nebula. These extremes in temperature remind us how diverse and strange the conditions in space can be. Neutron stars are another mind-blowing example of the extremes found in space. These incredibly dense remnants of massive stars that have gone supernova pack a huge amount of mass into a tiny space. A neutron star is typically only about 12 miles in diameter, but it can have a mass up to twice that of the Sun. This means that a sugar cube-sized amount of neutron star material would weigh around 1 billion tons on Earth. Neutron stars also have incredibly strong magnetic fields, billions of times stronger than Earth's, and they can spin at dizzying speeds, sometimes hundreds of times per second. These rapidly spinning neutron stars are known as pulsars, and they emit beams of radiation that sweep across space like cosmic lighthouses. Perhaps one of the most counterintuitive facts about space is that it has no true center. While we often think of the Big Bang as an explosion from a single point, it wasn't an explosion in space. It was an expansion of space itself. The Big Bang happened everywhere at once, meaning every point in the universe was the center of the expansion. As a result, space is isotropic, meaning it looks roughly the same in every direction, without a central point of reference. The concept of time and space is equally mind-bending. Time doesn't flow at a constant rate throughout the universe. Instead, it's relative, meaning it can be stretched or compressed depending on the strength of gravity, or how fast you're moving. This is a direct consequence of Einstein's theory of relativity. For example, time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been experimentally confirmed on Earth using precise atomic clocks. In the stronger gravitational field near Earth's surface, clocks tick more slowly than they do in space. On a larger scale, near massive objects like black holes, time dilation becomes even more pronounced, meaning time essentially stands still near the event horizon of a black hole. Gravity, which we often take for granted on Earth, works in strange and unexpected ways in space. For instance, the gravitational force between two objects decreases with the square of the distance between them, meaning that as objects get farther apart, the gravitational pull between them weakens rapidly. In the microgravity environment of space, astronauts experience what's known as free fall. Because both the astronaut and the spacecraft are falling toward Earth at the same rate, astronauts feel weightless, giving them the sensation of floating. On a larger cosmic scale, galaxies are bound together by gravity, forming massive structures known as galaxy clusters. The Milky Way is part of the local group, a small cluster of galaxies that includes the Andromeda Galaxy, the Large and Small Magellanic Clouds, and about 50 other smaller galaxies. These galaxy clusters are, in turn, part of even larger structures called superclusters. The local group is part of the Virgo supercluster, which is part of the larger Laniakea supercluster, a vast network of galaxies and clusters stretching over 500 million light-years. The scale of these cosmic structures is truly staggering. Within the Laniakea supercluster, galaxies are not randomly scattered but are connected by a vast cosmic web of filaments, made up of gas and dark matter. Between these filaments lie enormous voids, regions of space that are nearly empty of matter. This large-scale structure of the universe resembles a web or sponge, with galaxies clustered along the filaments, and vast empty spaces in between. The formation of this cosmic web is governed by the distribution of dark matter, which serves as the scaffolding for galaxies to form and evolve. Galaxies themselves are fascinating objects, each one containing billions or even trillions of stars, planets, and other celestial bodies. Our galaxy, the Milky Way, is a barred spiral galaxy with a diameter of about 100,000 light-years. It contains an estimated 100 to 400 billion stars, along with vast amounts of gas, dust, and dark matter. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A*, which has a mass of about 4 million times that of the Sun. Most large galaxies, including the Milky Way, are thought to harbor supermassive black holes at their centers, although the exact role these black holes play in the formation and evolution of galaxies is still a topic of ongoing research. Another incredible fact about space is the sheer diversity of exoplanets that have been discovered. Exoplanets are planets that orbit stars outside our solar system, and to date, thousands of them have been confirmed, with many more candidates awaiting confirmation. These exoplanets come in all shapes and sizes, ranging from Earth-like rocky planets to gas giants larger than Jupiter. Some exoplanets orbit their stars so closely that their surfaces are scorching hot, while others are located in the freezing outer regions of their star systems. There are also, rogue planets that drift through space without orbiting any star at all, having been ejected from their parent star systems. One of the most interesting types of exoplanets are those located in the habitable zone, also known as the Goldilocks zone. This is the region around a star where conditions might be just right for liquid water to exist, which is considered a key ingredient for life as we know it. While we have yet to discover definitive signs of life on any exoplanet, the discovery of potentially habitable worlds raises the tantalizing possibility that life could exist elsewhere in the universe. One such exoplanet that has captured the imagination of scientists is Proxima Centauri b, which orbits the star Proxima Centauri, the closest star to our solar system. Located just over 4 light-years away, Proxima Centauri b is in the habitable zone of its star, and although the conditions on the planet are still largely unknown, it represents one of the best chances we have of finding a potentially habitable world beyond our solar system. Another fascinating fact about space is the phenomenon of gravitational lensing. This occurs when a massive object, such as a galaxy or a cluster of galaxies, bends the light from objects behind it due to its strong gravitational field. This bending of light can create multiple images of the same distant object, as well as magnify it, allowing astronomers to study objects that would otherwise be too faint or far away to see. Gravitational lensing has become a powerful tool in astrophysics, helping scientists discover distant galaxies, map the distribution of dark matter, and even detect exoplanets. Speaking of light, it's important to note that when we observe distant objects in space, we are actually looking back in time. Because light takes time to travel, the farther away an object is, the older the light we are seeing. For example, when we look at the Andromeda Galaxy, we are seeing it as it was about 2.5 million years ago because that's how long it took the light to reach us. Similarly, when we observe the light from distant stars and galaxies, we are looking back billions of years into the past, giving us a glimpse of what the universe was like shortly after the Big Bang. The fact that space allows us to look back in time raises intriguing questions about the nature of the universe. One of the biggest mysteries in cosmology is the question of what lies beyond the observable universe. While we can see light from objects as far as 13.8 billion years ago, the universe is likely much larger than what we can observe. Some scientists even speculate that there could be multiple universes, or a multiverse, with each universe having its own physical laws and constants. This idea, while still speculative, has gained traction in some theoretical physics models, and if true, it would completely change our understanding of reality. Another mind-blowing concept in space is the idea of wormholes. These are hypothetical tunnels through spacetime that could, in theory, connect distant parts of the universe, or even different universes. Wormholes are predicted by Einstein's theory of general relativity, but so far, there is no experimental evidence to support their existence. If wormholes do exist, they could potentially allow for faster-than-light travel, or even time travel. However, the conditions required to create and stabilize a wormhole are far beyond our current technological capabilities. One of the most visually stunning phenomena in space is the aurora, or the northern and southern lights, which occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. While auroras are most commonly seen near the polar regions of Earth, similar light displays occur on other planets as well. For example, Jupiter and Saturn have their own versions of auroras, caused by interactions between their strong magnetic fields and the solar wind. These planetary auroras can be even more spectacular than those on Earth, with bright displays of ultraviolet and infrared light. Another mesmerizing fact about space involves the immense storms that rage across planets in our own solar system. For instance, Jupiter's Great Red Spot is a massive storm that has been swirling for at least 400 years. This giant anticyclonic storm is so large that 3 Earths could fit within it. The winds inside the Great Red Spot reach speeds of up to 400 miles per hour, and yet, despite centuries of observation, scientists are still unsure why it has persisted for so long. Jupiter's atmosphere itself is a chaotic mix of storms and wind bands, with lightning that is much more powerful than anything on Earth. Meanwhile, Saturn has its own version of massive storms, including the mysterious hexagonal storm pattern at its north pole, a six-sided jet stream that continues to baffle scientists. Another planetary storm of note is found on Neptune, where the winds are the fastest in the solar system, reaching speeds of up to 1,200 miles per hour. This is particularly astonishing given that Neptune is so far from the Sun, and its atmosphere should be relatively calm due to the lack of solar energy. Yet the planet remains a turbulent world of freezing temperatures and ferocious winds. Let's move away from planets and consider another type of celestial body, asteroids. Space is filled with these rocky objects, and while many are relatively small, some asteroids are truly colossal. One of the largest known asteroids is Ceres, which is also classified as a dwarf planet due to its size. Ceres, located in the asteroid belt between Mars and Jupiter, is about 600 miles in diameter. It even has its own thin atmosphere and features mysterious bright spots, which are thought to be deposits of salts left over from water activity. The idea that water, even in small amounts, could exist on such a barren rock opens up exciting possibilities for understanding the presence of water throughout the solar system. Asteroids are also responsible for one of the most significant events in Earth's history, the impact that led to the extinction of the dinosaurs around 66 million years ago. The Chicxulub asteroid, estimated to be around 6 miles wide, struck Earth with such force that it caused massive climate disruptions, wiping out about 75% of all life. This catastrophic event serves as a reminder of the potential threat that near-Earth objects pose to life on our planet. To this day, space agencies around the world are working to track potentially hazardous asteroids and develop methods to deflect or mitigate an impact should one be on a collision course with Earth. Space is also home to some truly bizarre and mind-bending phenomena, such as cosmic rays. These high-energy particles originate from outside our solar system and travel through space at nearly the speed of light. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles that can be detected on the ground. The origin of some of these cosmic rays is still unknown, and understanding their source is one of the many challenges facing astrophysicists today. Some cosmic rays are thought to come from supernovae, while others may originate from even more energetic events, such as the collisions of galaxies or the activity around supermassive black holes. On an even more exotic level, there are strange hypothetical particles like dark matter and dark energy. These mysterious substances make up the vast majority of the universe, yet they are invisible and do not interact with light, making them incredibly difficult to detect. Dark matter is believed to account for about 85% of the matter in the universe and is thought to hold galaxies together through its gravitational influence. However, despite decades of research, scientists have yet to directly observe dark matter. Similarly, dark energy, which makes up about 70% of the universe, is thought to be responsible for the accelerated expansion of the universe. Together, dark matter and dark energy dominate the cosmic landscape, yet we still know very little about their true nature. One particularly eerie aspect of space is the phenomenon known as black holes. These objects are formed when massive stars collapse under their own gravity, creating a region where gravity is so strong that not even light can escape. The boundary of this region is called the event horizon, and once something crosses this boundary, it is lost to the black hole forever. The idea of an object from which nothing can escape is mind-boggling enough, but black holes also play a crucial role in shaping the universe. They influence the formation of galaxies, bend light around them due to their immense gravitational pull, and in some cases, they can even merge to create even larger black holes. These mergers release gravitational waves, ripples in spacetime that can be detected by instruments on Earth, giving us new ways to study these enigmatic objects. The concept of a black hole is further complicated by the idea of Hawking radiation, named after physicist Stephen Hawking. According to Hawking's theory, black holes are not entirely black. They can slowly emit radiation over time due to quantum effects near the event horizon. This radiation causes black holes to lose mass and eventually evaporate completely, though for most black holes, this process would take longer than the current age of the universe. Hawking radiation presents a fascinating intersection between quantum mechanics and general relativity, two of the most fundamental yet seemingly incompatible theories in modern physics. Speaking of the intersection of theories, one of the greatest mysteries in physics today is the quest to unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While the standard model of particle physics successfully describes three of these forces, gravity remains the odd one out. Scientists are working on theories like string theory and loop quantum gravity in an attempt to unify these forces into a single framework, which could potentially lead to a theory of everything. If such a theory is discovered, it could radically change our understanding of space, time, and the universe as a whole. Another mind-blowing fact about space is the phenomenon of tidal forces. These are the result of gravitational interactions between celestial bodies and can lead to dramatic effects. For instance, the Moon's gravitational pull on Earth causes the ocean tides, and over time, it has also caused the Moon to become tidally locked, meaning the same side of the Moon always faces Earth. On a much larger scale, tidal forces from black holes can stretch and compress objects as they approach the event horizon, a process often referred to as spaghettification. In this scenario, an object falling into a black hole would be stretched into a long, thin shape before ultimately being torn apart by the extreme gravitational forces. Beyond the scientific phenomena, space is also full of strange and unexplained signals. One of the most famous is the WOW signal, a brief, strong radio signal detected by a radio telescope in 1977. The signal appeared to come from the direction of the constellation Sagittarius and lasted for 72 seconds. Despite numerous attempts to find the source of the WOW signal, it has never been detected again, and its origin remains a mystery. Some have speculated that it could have been a signal from an extraterrestrial civilization, though there is no concrete evidence to support this theory. While the WOW signal remains unexplained, scientists continue to search for signs of extraterrestrial life through programs like SETI, Search for Extraterrestrial Intelligence. By scanning the skies for radio signals or other forms of communication that might indicate the presence of intelligent life, SETI hopes to answer one of the most profound questions of all: are we alone in the universe? Given the vast number of stars and planets in the galaxy, it seems statistically likely that life exists elsewhere, yet so far, we have not found any definitive evidence. Another intriguing aspect of space is the way it challenges our understanding of what is possible. For example, there are theories that suggest the universe could be infinite, meaning it goes on forever with no boundaries. If true, this would mean that somewhere out there, far beyond the observable universe, there could be regions of space that are completely different from anything we've ever imagined. Some models even suggest that different physical laws could apply in these regions, creating parallel universes with entirely different realities. Another incredible aspect of space is the possibility of multiverses, a mind-boggling idea that has fascinated both scientists and philosophers alike. The multiverse theory posits that our universe is just one of many, potentially infinite universes, each with its own unique set of physical laws, constants, and structures. These alternate universes could range from being nearly identical to ours to being completely different, with entirely distinct forms of matter, energy, and dimensions. The concept of a multiverse arises from several branches of physics, including quantum mechanics and cosmology, and although it remains purely speculative, it offers tantalizing possibilities for the nature of reality itself. One variant of the multiverse theory comes from string theory, which suggests that there may be multiple dimensions beyond the familiar three spatial dimensions and time. In string theory, the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings can vibrate in different ways, corresponding to different particles, and in some versions of string theory, there are as many as 11 dimensions. These extra dimensions are hidden from us because they are curled up at incredibly small scales, but they could still play a crucial role in shaping the universe. In this framework, different universes could arise from different ways these dimensions are configured. Another source of the multiverse idea comes from the concept of cosmic inflation, a rapid expansion of the universe that occurred in the first fraction of a second after the Big Bang. According to inflationary theory, some regions of space could have stopped inflating while others continued, leading to the creation of bubble universes. Each of these bubble universes would be isolated from the others, with its own distinct properties. This idea has led to the notion of the inflationary multiverse, where countless universes could exist within an ever-expanding cosmic foam. One particularly thought-provoking aspect of the multiverse hypothesis is the idea that in an infinite universe or multiverse, everything that can happen, no matter how unlikely, will happen somewhere. This includes the possibility that somewhere out there, in a distant universe or a different region of space, there could be an exact copy of you, living a life that is either slightly or radically different from your own. The sheer scale of this concept is enough to challenge even the most expansive imaginations. Let's return now to a more familiar part of space: stars. Stars are the engines of the universe, producing light and heat through nuclear fusion, and they come in an astonishing variety of sizes, colors, and temperatures. One of the most fascinating types of stars is the neutron star, which forms when a massive star undergoes a supernova explosion and its core collapses. Neutron stars are incredibly dense, with a mass about 1.4 times that of the Sun packed into a sphere only about 12 miles across. A single teaspoon of neutron star material would weigh about 10 million tons on Earth. Some neutron stars are also pulsars, which are rapidly spinning stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like the beams of a lighthouse, and if one of the beams points toward Earth, we can detect it as a regular pulse of radio waves or other radiation. Pulsars are some of the most precise clocks in the universe, with some spinning hundreds of times per second. These objects are so stable that scientists use them to test the limits of general relativity and search for gravitational waves. Another type of extreme star is the magnetar, a type of neutron star with an extraordinarily strong magnetic field. Magnetars have magnetic fields billions of times stronger than that of Earth, and when they undergo a starquake, a shift in their crust, they can release powerful bursts of gamma rays. These bursts are some of the most energetic events in the universe, and while they only last for a few seconds, they can release more energy than the Sun produces in 100,000 years. Yet, not all stars end their lives in such a dramatic fashion. Some, like our Sun, will eventually shed their outer layers and leave behind a hot, dense core known as a white dwarf. Over billions of years, this white dwarf will gradually cool and fade, becoming a black dwarf, though none exist yet because the universe is not old enough for any white dwarfs to have cooled completely. Even in death, stars continue to shape the cosmos, seeding space with the heavy elements needed for planets and life. On the other end of the stellar spectrum are the massive stars that go out in a blaze of glory. When a star with more than about 8 times the mass of the Sun runs out of fuel, its core collapses under its own gravity, leading to a supernova explosion. These explosions are some of the most powerful events in the universe, briefly outshining entire galaxies and dispersing elements like carbon, oxygen, and iron into space. These elements are the building blocks of planets, moons, and even life itself. In a very real sense, we are made of star stuff, as the famous astronomer Carl Sagan once said. The supernovae of very massive stars can also lead to the formation of black holes, and these black holes are not just passive objects sitting in space. They actively shape their surroundings through their powerful gravitational pull. Some black holes, known as stellar black holes, are formed from individual stars, while others, known as supermassive black holes, reside at the centers of galaxies and have masses millions or even billions of times that of the Sun. These supermassive black holes are thought to play a crucial role in the evolution of galaxies, and they are surrounded by disks of gas and dust that can heat up to millions of degrees as they spiral into the black hole. In some cases, black holes can also create jets of high-energy particles that shoot out into space at nearly the speed of light. These jets can stretch for thousands of light years and are some of the most energetic phenomena in the universe. Despite their reputation as cosmic vacuum cleaners, black holes are actually responsible for some of the most spectacular displays of energy in space. While black holes may be some of the most mysterious objects in the universe, there is another cosmic enigma that is just as perplexing: quasars. Quasars are the brightest objects in the universe, powered by supermassive black holes at the centers of galaxies. As matter falls into the black hole, it heats up and emits enormous amounts of radiation, making quasars visible across vast distances. Some quasars are so bright that they can outshine their entire host galaxy. The light we see from quasars comes from billions of years ago, providing a glimpse into the distant past of the universe. In fact, one of the most mind-blowing facts about space is that when we look up at the night sky, we are looking back in time. Light from distant stars and galaxies takes time to reach us, and because space is so vast, the light we see today could have traveled for millions or even billions of years. When we observe distant galaxies, we are seeing them as they were in the distant past, and in some cases, we are looking at galaxies that no longer exist in their current form. This concept, known as look-back time, allows astronomers to study the history of the universe and understand how galaxies and stars have evolved over time. As we peer deeper into space, we encounter one of the most profound mysteries of all: the nature of the universe's expansion. In 1929, astronomer Edwin Hubble made the groundbreaking discovery that the universe is expanding. He observed that distant galaxies are moving away from us, and the farther away a galaxy is, the faster it is receding. This discovery led to the formulation of Hubble's law, which states that the rate at which a galaxy moves away from us is proportional to its distance. But what's even more astounding is that the expansion of the universe is not slowing down, as one might expect, but is actually accelerating. This discovery, made in the late 1990s, came as a complete surprise to scientists, and it has led to the hypothesis of dark energy. Dark energy is thought to make up about 70% of the universe, yet its true nature remains one of the greatest mysteries in cosmology. It seems to be responsible for the accelerated expansion, but we still don't know what it is or how it works. The concept of dark energy represents one of the most profound challenges to our understanding of the universe. Unlike dark matter, which we believe has gravitational effects that can be observed, dark energy appears to be even more elusive. It's as if the universe has some kind of invisible force, a repulsive energy, that is pushing galaxies apart at an accelerating rate. What makes this so bewildering is that the very fabric of space itself seems to be stretching. As space expands, new space appears, and this causes distant galaxies to move away from each other faster and faster. The idea that empty space could possess its own energy, known as the cosmological constant, is difficult to comprehend, but it's currently the best explanation we have for the observed acceleration of the universe's expansion. The discovery of dark energy has forced physicists and astronomers to rethink many long-held assumptions about the cosmos. For instance, prior to its discovery, many believed that the expansion of the universe would eventually slow down and perhaps reverse, leading to a big crunch, where the universe would collapse back in on itself. But with the discovery of dark energy, this scenario seems less likely. Instead, the universe may continue to expand forever, with galaxies growing farther apart, and the cosmos becoming increasingly cold and dark as stars burn out, and new ones fail to form. This possible future, sometimes called the Big Freeze, paints a rather bleak picture of the universe's fate. However, there are still many unanswered questions. For one, while we can infer the presence of dark energy from its effects, we still don't know exactly what it is. Some theories suggest that it could be a new kind of field that permeates space, while others propose that it might be a sign that our understanding of gravity is incomplete. Whatever the answer, solving the mystery of dark energy could revolutionize our understanding of physics and cosmology. Equally mysterious is dark matter, another invisible component of the universe. While dark energy is responsible for pushing the universe apart, dark matter seems to act as a cosmic glue, holding galaxies together. In fact, without dark matter, many galaxies, including our own, would not be able to maintain their structure. The stars and gas we can see in galaxies are simply not enough to account for the gravitational forces required to keep them from flying apart. Dark matter does not emit, absorb, or reflect light, which is why we cannot see it directly. Instead, we detect its presence through its gravitational effects. For example, when astronomers observe the rotation of galaxies, they find that the outer stars are moving much faster than they should be based on the amount of visible matter. The only explanation for this is that there is additional unseen mass, dark matter, exerting gravitational force. Despite its importance in the structure of the universe, we still don't know what dark matter is made of. Some theories suggest that it could be composed of particles called WIMPs, weakly interacting massive particles, while others propose exotic particles or modifications to our understanding of gravity. Numerous experiments are underway to detect dark matter directly, but so far, it has remained frustratingly elusive. If dark matter and dark energy make up most of the universe, what about the part we can actually see? Surprisingly, only about 5% of the universe consists of ordinary matter, the stuff that makes up stars, planets, and everything we're familiar with. This means that most of the cosmos is made up of something completely invisible and mysterious, a fact that continues to astonish scientists. This brings us to another mind-blowing fact about space: the cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and serves as a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe was a hot, dense soup of particles, but as it expanded and cooled, it reached a point where atoms could form, allowing light to travel freely through space. This light has been stretching and cooling ever since, and today it is seen as microwave radiation, just a few degrees above absolute zero. The discovery of the CMB in 1965 was one of the most important breakthroughs in cosmology, providing strong evidence for the Big Bang theory. By studying the tiny fluctuations in the CMB, scientists have been able to learn a great deal about the early universe, including its age, composition, and structure. These fluctuations represent slight variations in the density of matter in the early universe, which eventually gave rise to galaxies and other large-scale structures we see today. One of the remarkable things about the CMB is that it is incredibly uniform, with only tiny variations in temperature. This uniformity has led to questions about how regions of the universe that are so far apart could have the same temperature, given that they could not have exchanged information or energy due to the limits of the speed of light. This problem, known as the horizon problem, is one of the reasons why scientists developed the theory of cosmic inflation, which suggests that the universe underwent a rapid expansion in its earliest moments, smoothing out any initial irregularities. Moving on from the cosmic scale, let's turn our attention to one of the most curious and fundamental phenomena in the universe: black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity at the end of their life cycles, creating an object with an extremely dense core. The boundary of a black hole is known as the event horizon, and once something crosses this boundary, it is forever trapped inside. What lies beyond the event horizon is a mystery. According to general relativity, the core of a black hole, or singularity, is a point of infinite density where the laws of physics break down. However, this is likely not the whole story, and many physicists believe that a more complete theory of gravity, perhaps involving quantum mechanics, is needed to fully understand black holes. One of the most fascinating ideas about black holes is that they may not just be destructive objects, but could also play a role in the creation of new universes. Some speculative theories suggest that the interior of a black hole could be connected to another region of space or even another universe, with the black hole serving as a kind of wormhole. While this idea remains purely theoretical, it raises the possibility that black holes could be gateways to other realms of reality. In recent years, our understanding of black holes has taken a giant leap forward thanks to the detection of gravitational waves, ripples in spacetime caused by the collision of massive objects like black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first ever detection of gravitational waves from the merger of two black holes. This discovery opened a new window on the universe, allowing scientists to observe cosmic events that were previously invisible. Gravitational waves are a direct prediction of Einstein's theory of general relativity, and their detection has provided a new way to study the universe. By observing these waves, scientists can learn about the masses, spins, and other properties of merging black holes and neutron stars. In the future, gravitational wave astronomy could reveal even more about the mysterious nature of black holes and other extreme objects. In addition to black holes, space is also home to some truly bizarre and exotic phenomena. One of these is the possibility of white holes, the theoretical opposite of black holes. Whereas black holes are regions where nothing can escape, white holes are regions where nothing can enter. According to some solutions of Einstein's equations, a white hole could theoretically exist, but there is no evidence that any have ever been observed. However, white holes remain a fascinating possibility in the realm of theoretical physics. Another strange phenomenon is the existence of cosmic strings, hypothetical one-dimensional defects in spacetime that could have formed in the early universe. These strings would be incredibly thin, with a width much smaller than a proton, but they could stretch across vast distances, perhaps even across the entire universe. If they exist, cosmic strings could create gravitational effects that bend light and distort spacetime, making them detectable through astronomical observations. In fact, the idea of spacetime itself is one of the most mind-blowing concepts in modern physics. According to general relativity, space and time are not separate entities but are instead intertwined in a four-dimensional fabric known as spacetime. Massive objects like stars and planets warp this fabric, creating the effect we perceive as gravity. The more massive an object, the more it bends spacetime, and this curvature affects the paths of objects moving through space. This curvature of spacetime, as described by Einstein's theory of general relativity, fundamentally changed our understanding of gravity. Instead of viewing gravity as a force that objects exert on each other, it's now understood as a result of the geometry of spacetime itself. Imagine placing a heavy object on a trampoline. It causes the fabric of the trampoline to bend, and smaller objects will roll towards it because of that curvature. In a similar way, planets orbit stars and stars orbit the center of galaxies due to the warping of spacetime. What's even more mind-blowing is that spacetime can be warped so dramatically that time itself behaves differently near massive objects. Time dilation is one of the most counterintuitive aspects of general relativity. It means that time runs slower in stronger gravitational fields, such as near a black hole. If an astronaut were to approach a black hole, their clock would tick slower relative to someone far away from the black hole. In fact, if they were to reach the event horizon of the black hole, time would appear to stop altogether for an outside observer. This effect is not just theoretical, it has been measured experimentally in less extreme environments, such as in Earth's gravitational field, where clocks run slightly slower on the surface than at higher altitudes. Time dilation also occurs at high speeds, as predicted by Einstein's theory of special relativity. As an object approaches the speed of light, time slows down for it relative to a stationary observer. This means that for astronauts traveling close to the speed of light, time would pass much more slowly than for people back on Earth. In theory, this could allow for some form of time travel to the future, where an astronaut could travel at near light speed for what feels like a few years to them but return to Earth to find that decades or even centuries have passed. The speed of light itself is a fundamental limit in the universe. According to special relativity, nothing can travel faster than light in a vacuum, which moves at about 299,792 kilometers per second, 186,282 miles per second. This speed limit has profound implications for our understanding of space and time. For instance, because light from distant galaxies takes millions or even billions of years to reach us, when we look at the night sky, we are essentially looking back in time. Some of the stars and galaxies we see may no longer exist in their current form, but we still see their light because of the immense distances involved. One of the greatest mysteries in modern physics involves trying to reconcile general relativity, which describes the large-scale structure of the universe, with quantum mechanics, which governs the behavior of particles at the smallest scales. These two theories are incredibly successful in their respective domains but seem to be fundamentally incompatible. General relativity breaks down when trying to describe extremely small regions of space, such as inside black holes or at the moment of the Big Bang, where quantum effects become important. Likewise, quantum mechanics doesn't incorporate gravity in the same way that it does other forces. A unified theory that can describe both the large-scale and small-scale structure of the universe, sometimes referred to as a theory of everything, remains one of the holy grails of physics. One of the candidates for such a theory is string theory, which suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the various particles and forces in the universe. What makes string theory so appealing is that it naturally incorporates gravity, and can describe both the large-scale and small-scale structure of the universe. However, string theory is still very much in the realm of theoretical physics, and it has yet to be confirmed by experiments. String theory also suggests that there could be more dimensions of space than the three we're familiar with. According to the theory, there could be additional dimensions that are curled up so tightly that we don't notice them in our everyday experience. If these extra dimensions exist, they could have profound implications for our understanding of the universe, and could help explain some of the unresolved mysteries in physics, such as the nature of dark matter and dark energy. Another mind-blowing idea is the multiverse hypothesis, which suggests that our universe may be just one of many universes, each with its own set of physical laws and constants. According to some interpretations of quantum mechanics and string theory, there could be an infinite number of parallel universes, each with different properties. In some of these universes, the laws of physics might be entirely different from our own, while in others, they might be similar but with slight variations. This idea raises profound questions about the nature of reality and our place in the cosmos. Could there be other versions of ourselves living in parallel universes, experiencing different outcomes in their lives? The possibility of a multiverse also has implications for the fine-tuning of the universe. Many aspects of our universe, such as the strength of the fundamental forces and the masses of particles, seem to be finely tuned to allow for the existence of life. If these constants were even slightly different, the universe might not support life as we know it. One explanation for this fine-tuning is that we live in a multiverse, and we just happen to be in a universe where the conditions are right for life to exist. In other words, the apparent fine-tuning could be a result of a kind of cosmic lottery, with countless other universes where life is not possible. The search for life beyond Earth is another topic that continues to capture the imagination of scientists and the public alike. With the discovery of thousands of exoplanets, planets orbiting stars outside our solar system, the possibility of finding life on other worlds seems more likely than ever before. Some exoplanets are located in the habitable zone of their stars, where conditions might be right for liquid water to exist, a key ingredient for life as we know it. However, the search for extraterrestrial life is not limited to planets. Moons like Europa, which orbits Jupiter, and Enceladus, which orbits Saturn, have subsurface oceans that could harbor life. These moons are covered in thick ice, but evidence suggests that there may be hydrothermal vents on their ocean floors, similar to those found in Earth's oceans, which could provide the energy needed to sustain life. In addition to the search for microbial life, there is also the ongoing quest to detect intelligent extraterrestrial civilizations. The Search for Extraterrestrial Intelligence (SETI) program has been listening for radio signals from other civilizations for decades, but so far, no definitive evidence has been found. However, the discovery of even microbial life elsewhere in the solar system or the galaxy would have profound implications for our understanding of life's potential in the universe. Another exciting development in the exploration of space is the possibility of humans becoming an interplanetary species. With missions to Mars on the horizon, the idea of humans living and working on other planets is no longer the stuff of science fiction. Mars is considered the most viable candidate for human colonization because of its relatively mild climate, compared to other planets, and the presence of water in the form of ice. However, there are still many challenges to overcome before humans can establish a permanent presence on Mars, including the need to develop technologies for long-term survival in such a harsh environment. Terraforming Mars, the process of making the planet more Earth-like, has been proposed as a long-term solution for making Mars habitable for humans. This could involve releasing greenhouse gases to warm the planet and create a thicker atmosphere, melting the polar ice caps to provide water, and even introducing plants and microorganisms to produce oxygen. While these ideas are still far from being realized, they represent one of the most ambitious goals for humanity's future in space. In the distant future, humans could explore even more exotic locations in the universe. One of the most intriguing possibilities is the colonization of planets orbiting other stars, known as exoplanets. While the distances to even the closest exoplanets are mind-bogglingly vast, advancements in propulsion technology could one day make interstellar travel a reality. Concepts such as light sails, which use the pressure of light from a powerful laser to propel a spacecraft, could allow us to travel to nearby stars in a matter of decades rather than centuries. Interstellar travel, though still far beyond our current technological capabilities, has been the focus of theoretical research and speculation for decades. One of the most exciting proposals is the idea of a warp drive, a concept inspired by Einstein's general theory of relativity. A warp drive would allow a spacecraft to travel faster than the speed of light by compressing the space in front of it and expanding the space behind it, effectively moving the ship without violating the laws of physics. This idea, while still speculative, has captured the imagination of scientists and science fiction enthusiasts alike. If realized, it could open up the entire galaxy to human exploration, making journeys to distant stars possible within a human lifetime. But even if warp drives or other advanced propulsion technologies remain out of reach, robotic probes could still play a major role in exploring the universe. One of the most intriguing ideas is the concept of von Neumann probes, self-replicating machines that could be sent to explore the galaxy. These probes would travel to distant star systems, gather raw materials, and use them to create copies of themselves. The new probes would then continue the journey, spreading out across the galaxy in an exponentially growing network. This kind of exploration could allow us to learn about the universe on a scale that would be impossible with human astronauts alone. The vastness of space also presents another fascinating aspect of the universe: the sheer number of stars and galaxies. In our observable universe alone, there are estimated to be around 100 billion galaxies, each containing hundreds of billions of stars. This means that there are more stars in the observable universe than there are grains of sand on all the beaches of Earth. Each of these stars could potentially host planets, raising the possibility of trillions of planets throughout the universe. The scale of the universe is so immense that it's difficult to comprehend, and it suggests that our solar system is just a tiny speck in the grand scheme of things. Despite the enormous number of stars and galaxies, the universe is mostly empty space. The average distance between stars in our galaxy is about 4 light-years, and the distances between galaxies are even more staggering. The nearest galaxy to the Milky Way, the Andromeda Galaxy, is about 2.5 million light-years away. This vast emptiness means that, even if intelligent civilizations exist elsewhere in the universe, the chances of us encountering them are extremely slim due to the vast distances involved. Another fascinating aspect of space is the discovery of exoplanets with bizarre and extreme environments. Some exoplanets, known as hot Jupiters, are gas giants that orbit very close to their stars, with surface temperatures reaching thousands of degrees. Others, like rogue planets, are not bound to any star at all and drift through interstellar space. There are even planets where it rains molten glass or where winds blow at speeds of thousands of miles per hour. These extreme conditions challenge our understanding of what a planet can be and raise questions about the diversity of planetary systems in the universe. One of the strangest types of planets is the so-called super-Earth, a class of exoplanets that are larger than Earth but smaller than Neptune. These planets could have atmospheres and climates very different from those of any planet in our solar system. Some super-Earths may have thick, hydrogen-rich atmospheres, while others could have vast oceans covering their entire surfaces. The discovery of these planets has opened up new possibilities for the search for life, as some super-Earths could have conditions suitable for life to evolve. Another mind-blowing idea is the possibility of artificial megastructures built by advanced civilizations. One such concept is the Dyson sphere, a hypothetical structure that could be built around a star to capture its energy. A Dyson sphere would allow a civilization to harness nearly all of the energy output of its star, potentially providing vast amounts of power. While no evidence of such structures has been found, The idea has inspired both scientific and science fiction discussions about the possibilities for advanced civilizations in the universe. One of the most important recent discoveries in astronomy is the detection of gravitational waves. These ripples in spacetime were first predicted by Einstein's theory of general relativity, but it wasn't until 2015 that they were directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are produced by violent events in the universe, such as the collision of black holes or neutron stars. These waves carry information about the events that produce them, allowing scientists to study some of the most extreme environments in the universe. The detection of gravitational waves has opened up a new way of observing the universe, complementing traditional methods like telescopes that observe electromagnetic radiation, light. The discovery of gravitational waves has also provided new insights into the nature of black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. When two black holes collide, they merge to form a larger black hole, releasing a burst of gravitational waves in the process. These events are incredibly powerful, with the energy released in gravitational waves being equivalent to the mass of several suns. By studying these waves, scientists can learn more about the properties of black holes and how they interact with each other. One of the most mind-blowing properties of black holes is the existence of the event horizon, the boundary beyond which nothing can escape. Once an object crosses the event horizon, it is thought to be lost forever, pulled inexorably towards the singularity at the center of the black hole. The singularity is a point of infinite density where the laws of physics, as we know them, break down. The existence of singularities raises profound questions about the nature of spacetime, and whether new physics is needed to describe what happens inside a black hole. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners that suck up everything in their vicinity. Objects need to get very close to a black hole to be pulled in, and outside the event horizon, the gravity of a black hole behaves just like the gravity of any other massive object. In fact, if the Sun were replaced by a black hole of the same mass, the planets would continue orbiting it in the same way, though they would no longer receive any light or heat. Black holes can also come in different sizes. Stellar mass black holes, which are formed from the collapse of massive stars, typically have masses a few times that of the Sun's supermassive black holes. On the other hand, can have masses millions or even billions of times that of the Sun. These giant black holes are thought to exist at the centers of most galaxies, including our own Milky Way. How these supermassive black holes formed is still a mystery, but they play a crucial role in shaping the galaxies around them. One of the most exciting discoveries in recent years is the observation of a black hole eating a star. When a star ventures too close to a black hole, it can be torn apart by the black hole's gravity in a process known as tidal disruption. The debris from the star forms a disk of material around the black hole, which emits intense radiation as it is gradually pulled into the black hole. These events are incredibly rare but provide valuable opportunities for studying black holes and the extreme environments around them. The concept of black holes has also led to speculation about the existence of wormholes, theoretical tunnels through spacetime that could connect distant regions of the universe. While no evidence for wormholes has been found, they are a legitimate solution to the equations of general relativity, and some physicists have speculated that they could allow for faster-than-light travel, or even time travel. However, most solutions for wormholes suggest that they would be highly unstable and collapse before anything could pass through them. Another fascinating concept that emerges from the study of black holes and wormholes is the idea of time dilation. This is an effect predicted by Einstein's theory of relativity, where time appears to pass more slowly in stronger gravitational fields or at higher speeds. Near a black hole, for example, time would pass much slower for an observer close to the event horizon compared to someone far away. This effect, known as gravitational time dilation, has been experimentally confirmed, though the effects are only noticeable near extremely massive objects like black holes. Time dilation also occurs at high velocities, as predicted by Einstein's theory of special relativity. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. This leads to one of the most mind-bending ideas in physics, time travel. In theory, if you were to travel at near light speeds for an extended period, time would pass much more slowly for you than for people on Earth. When you returned, you might find that decades or even centuries had passed, even though only a short amount of time had passed for you. While this kind of time travel into the future is theoretically possible, the extreme speeds and energy requirements make it far beyond our current technological capabilities. Speaking of time, the age of the universe is another astonishing fact to consider. The universe is estimated to be about 13.8 billion years old, based on measurements of the cosmic microwave background radiation and the expansion of the universe. This immense timescale is difficult to grasp, especially when compared to the relatively short history of human civilization. Our species has only existed for about 200,000 years, a mere blink of an eye in cosmic terms. The entire history of human civilization, from the first agricultural societies to the modern world, has taken place in just the last 10,000 years. In contrast, the universe has been evolving and changing for billions of years, with stars being born, living out their lifespans, and eventually dying in spectacular supernovae. The death of stars is one of the most dramatic events in the universe. When a massive star exhausts its nuclear fuel, it can undergo a supernova explosion, releasing more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. These explosions are not only visually stunning but also play a crucial role in the cosmic cycle of matter. The heavy elements created in the cores of stars, such as carbon, oxygen, and iron, are scattered into space by supernovae, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. In a very real sense, the atoms that make up our bodies were forged in the hearts of ancient stars that exploded long before our solar system was born. Another mind-blowing fact about space is the role of dark matter and dark energy in the universe. These mysterious substances make up the vast majority of the universe's mass-energy content, yet they remain largely unexplained. Dark matter is thought to make up about 27% of the universe's mass-energy content, while dark energy accounts for roughly 68%. This means that everything we can see, stars, planets, galaxies, and all other forms of visible matter, only makes up about 5% of the universe. Dark matter doesn't emit or interact with light, which is why we can't see it, but its gravitational effects are evident in the way galaxies rotate and in the large-scale structure of the universe. Without dark matter, galaxies would not have enough mass to hold together, and the universe as we know it would not exist. Dark energy, on the other hand, is even more mysterious. It is thought to be responsible for the accelerated expansion of the universe, which was first discovered in the late 1990s. Before this discovery, most scientists expected the expansion of the universe to slow down over time due to the gravitational pull of matter. However, observations of distant supernovae revealed that the expansion is actually speeding up, suggesting that some unknown force, dubbed dark energy, is driving this acceleration. The nature of dark energy is one of the biggest unsolved mysteries in cosmology, and understanding it could revolutionize our understanding of the universe. The accelerated expansion of the universe has profound implications for the future of the cosmos. If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate. Over time, galaxies will move farther and farther apart, eventually becoming so distant from each other that they will no longer be visible from Earth. This scenario, known as the Big Freeze, or heat death, suggests that the universe will become a cold, dark, and empty place, with all the stars burned out and all matter dispersed. While this grim fate is billions of years in the future, it highlights the impermanence of the universe and the ever-changing nature of cosmic evolution. Another strange and mind-blowing phenomenon is the idea of quantum mechanics in space. On the smallest scales, the universe behaves according to the bizarre rules of quantum mechanics, where particles can exist in multiple states at once and can even influence each other instantaneously across vast distances, a phenomenon known as quantum entanglement. While quantum effects are usually only noticeable at the microscopic level, they may also play a role in the large-scale structure of the universe. Some scientists have even speculated that the early universe was influenced by quantum fluctuations, tiny variations in energy that may have seeded the formation of galaxies and other cosmic structures. Quantum mechanics also leads to the idea of the multiverse, the possibility that our universe is just one of many universes that exist in a vast multiverse. According to some interpretations of quantum mechanics and cosmology, there could be an infinite number of universes, each with its own set of physical laws and constants. In some of these universes, the conditions might be similar to our own, while in others, they could be radically different. The multiverse concept is still highly speculative, but it raises profound questions about the nature of reality and our place in the cosmos. The concept of parallel universes has been popularized in science fiction, but it is also a serious topic of discussion among some physicists. One theory, known as the many worlds interpretation of quantum mechanics, suggests that every possible outcome of a quantum event actually occurs, but in different branches of the universe. This means that there could be countless parallel versions of ourselves, each living in a slightly different reality. While there is no direct evidence for the many worlds interpretation, it provides an intriguing way to think about the strange and counterintuitive nature of quantum mechanics. Another mind-blowing idea is the possibility of life elsewhere in the universe. Given the vast number of stars and planets, it seems likely that life could exist elsewhere, though no definitive evidence has been found yet. The search for extraterrestrial life has been one of the major goals of space exploration, with missions like NASA's Mars rovers and the upcoming James Webb Space Telescope designed to look for signs of life on other planets. Some scientists have even speculated that life might exist in extreme environments within our own solar system, such as the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. The discovery of even microbial life on another planet would be one of the most profound discoveries in human history, as it would suggest that life is not unique to Earth. If intelligent extraterrestrial civilizations exist, the implications would be even more staggering. The famous Fermi paradox asks why, if there are so many stars and planets in the universe, we have not yet detected any signs of intelligent life. Various explanations have been proposed, ranging from the idea that intelligent civilizations are extremely rare to the possibility that they are deliberately avoiding contact with us. The Fermi paradox remains one of the most intriguing mysteries in the search for extraterrestrial life. One possible explanation is that intelligent civilizations may be short-lived, either due to self-destruction through technology, environmental collapse, or other catastrophic events. This concept is often referred to as the Great Filter, a hypothetical stage in the evolution of life that is extremely difficult to pass. If the Great Filter is ahead of us, it suggests that humanity may face a significant challenge that could prevent us from becoming a long-lived, space-faring civilization. On the other hand, if the Great Filter is behind us, if it was something like the origin of life or the evolution of complex multicellular organisms, then we may already be in a unique position as one of the few intelligent species in the universe. This would mean that intelligent life is extraordinarily rare, which could explain why we haven't yet encountered any other civilizations. Yet another explanation for the Fermi paradox is the idea that advanced civilizations may be using forms of communication or technology that we do not yet understand. Just as early radio waves would have been invisible to our ancestors, it's possible that extraterrestrial civilizations are using technologies that are beyond our current comprehension. Alternatively, they may be deliberately avoiding detection, either because they view us as too primitive or because they follow some kind of prime directive of non-interference, much like the ethical considerations we ponder in relation to contact with indigenous cultures here on Earth. The concept of extraterrestrial civilizations leads to the mind-bending possibility of interstellar travel. Given the vast distances between stars, traveling to even the nearest stars would take thousands of years using current technology. However, advanced propulsion methods such as warp drives, wormholes, or other hypothetical technologies could make interstellar travel feasible. While these ideas remain speculative, they have been seriously considered by physicists and engineers as potential solutions to the challenges of space travel. One of the most famous ideas is the Alcubierre drive, a theoretical concept that involves warping spacetime to allow faster-than-light travel. In this concept, A spacecraft would create a bubble of spacetime around itself, contracting the space in front of it and expanding the space behind it. This would allow the spacecraft to move faster than light relative to distant observers, without violating the laws of physics. While the Alcubierre drive is purely theoretical at this point, it shows that faster-than-light travel may not be entirely impossible, at least in theory. Wormholes, another speculative idea, are hypothetical tunnels through spacetime that could connect distant points in the universe. In theory, a wormhole could allow instantaneous travel between two locations, regardless of the distance between them. While wormholes are a popular concept in science fiction, they are also a serious topic of study in theoretical physics. However, there are many challenges to making wormholes a reality, including the need for exotic forms of matter to stabilize them and the potential for extreme gravitational forces to destroy anything that tries to pass through. The sheer scale of space is another mind-blowing fact. The observable universe is estimated to be about 93 billion light-years in diameter, yet that's just the portion we can see. Beyond the observable universe, there may be regions of space that we will never be able to observe due to the finite speed of light and the continued expansion of the universe. This raises profound questions about the nature of the universe as a whole, whether it is infinite, finite, or something else entirely. The size of space also makes it difficult to comprehend the distances between celestial objects. For example, the nearest star to Earth, Proxima Centauri, is about 4.24 light-years away, meaning that light from Proxima Centauri takes over 4 years to reach us. To put that in perspective, if we could travel at the speed of light, a feat that current physics suggests is impossible, it would still take over 4 years to reach Proxima Centauri. In comparison, our solar system itself, encompassing the Sun and all its planets, is just a tiny speck within the vastness of our galaxy, the Milky Way, which is about 100,000 light-years in diameter. Our galaxy alone contains hundreds of billions of stars, each potentially hosting their own planetary systems, many of which could harbor life. The Milky Way is part of a local group of galaxies, which includes the Andromeda Galaxy and about 54 other smaller galaxies. The Andromeda Galaxy, located approximately 2.537 million light-years away, is on a collision course with the Milky Way. In about 4.5 billion years, our two galaxies are expected to merge into a single, larger galaxy. This cosmic event will not result in catastrophic collisions between stars, as the distances between stars are vast. Instead, the gravitational interactions will reshape both galaxies over eons, leading to a new galactic structure. Even on a smaller scale, the structure of our own solar system is breathtaking. The 8 planets, along with their moons, dwarf planets, asteroids, and comets, create a dynamic and complex environment. Each planet has its own unique characteristics. For example, Jupiter is the largest planet in our solar system, known for its Great Red Spot, a massive storm larger than Earth that has raged for centuries. Saturn, famous for its stunning rings, is composed primarily of hydrogen and helium and has a multitude of moons, including Titan, which has a thick atmosphere and lakes of liquid methane and ethane, making it one of the most intriguing places to search for life. Mars, often referred to as the Red Planet, has long fascinated scientists and the public alike. With its similarities to Earth, including seasons, polar ice caps, and a day length very close to ours, Mars has been the focus of numerous exploration missions. The presence of water in the form of ice and the discovery of seasonal dark streaks on its surface suggests that liquid water may exist, at least temporarily, under certain conditions. This has led to intense interest in Mars as a potential candidate for past or present life. The ongoing Mars missions, including rovers like Perseverance and Curiosity, aim to uncover evidence of ancient microbial life and collect samples for future return to Earth. These missions not only explore the geology and climate of Mars but also test technologies that may be essential for future human exploration, including in situ resource utilization, which could enable astronauts to use Martian materials for fuel and life support. Beyond our solar system lies the vast expanse of interstellar space, where stars and galaxies exist. The distances involved are so immense that they challenge our understanding of time and travel. To visualize this, consider that the light from the nearest galaxy, the Andromeda Galaxy, takes over 2.5 million years to reach us. This means that when we observe Andromeda today, we are seeing it as it was over 2.5 million years ago, long before modern humans ever walked the Earth. In fact, much of what we observe in the universe is light that has traveled vast distances, showing us the cosmos as it was in the distant past. The concept of cosmic background radiation is another profound aspect of space that further demonstrates this incredible scale of time and distance. The cosmic microwave background (CMB) radiation is a remnant of the Big Bang, the event that is believed to have created our universe approximately 13.8 billion years ago. This radiation is a faint glow of light that fills the universe and can be detected in every direction. It provides a snapshot of the early universe, offering insights into its origins and evolution. The CMB is a testament to the dynamic history of the cosmos and is instrumental in supporting the Big Bang theory. One might wonder about the fate of stars and the life cycle of the universe itself. When a star exhausts its nuclear fuel, its fate depends on its mass. Smaller stars, like our Sun, will swell into red giants and eventually shed their outer layers, leaving behind a dense core known as a white dwarf. Over billions of years, the white dwarf will cool and fade into a black dwarf, an endpoint that has yet to be observed in the universe due to its age. In contrast, massive stars undergo more dramatic deaths. After exhausting their fuel, they can explode in a supernova, an event that outshines entire galaxies for a brief period. The remnants of such explosions can form neutron stars or black holes, depending on the mass of the original star. Neutron stars are incredibly dense, packing a mass greater than that of the Sun into a sphere just a few kilometers in diameter. A sugar cube-sized amount of neutron star material would weigh as much as all of humanity combined. Black holes, on the other hand, represent regions of spacetime where gravity is so strong that nothing, not even light, can escape their pull. The boundary surrounding a black hole is known as the event horizon, beyond which events cannot be observed. The study of black holes challenges our understanding of physics, particularly at the intersection of quantum mechanics and general relativity. Theories suggest that black holes may emit radiation, known as Hawking radiation, due to quantum effects near the event horizon. This phenomenon implies that black holes could eventually evaporate over immense timescales, leading to intriguing questions about the information contained within them. When a black hole evaporates, does it destroy the information about the matter that fell into it, or does that information somehow escape? This is known as the black hole information paradox and remains an active area of research in theoretical physics. Moreover, the expansion of the universe, driven by dark energy, poses profound questions about its ultimate fate. As the universe continues to expand, galaxies will drift farther apart, and the stars within them will eventually burn out. Over trillions of years, the universe may become a dark, cold place devoid of any visible light, leading to the heat death scenario. In this distant future, all processes will cease, and the universe will reach a state of maximum entropy, where energy is evenly distributed, and no work can be performed. Yet, there are other potential scenarios for the universe's fate. One such theory is the Big Crunch, where the expansion of the universe eventually slows, halts, and reverses, causing everything to collapse back into a singularity. This concept contrasts with the current observations suggesting accelerated expansion due to dark energy. Another possibility is the Big Rip, where the expansion of the universe accelerates to the point that it tears apart galaxies, stars, and even atoms. In this scenario, the very fabric of spacetime itself would be disrupted, leading to a cataclysmic end. The questions surrounding the cosmos are not just limited to the physical properties of the universe. They also touch on existential and philosophical issues. For example, if there are indeed multiple universes, each with its own laws of physics, what does that mean for our understanding of reality? Do these universes coexist alongside ours, or are they entirely separate realms? The implications of a multiverse challenge our notions of uniqueness and the nature of existence itself. Furthermore, the possibility of life in the cosmos forces us to reconsider what it means to be human and our place in the universe. If we discover microbial life on another planet, or even evidence of intelligent civilizations, it could reshape our understanding of life's origins and evolution. Such discoveries would challenge our anthropocentric worldview and encourage a deeper exploration of the ethical considerations surrounding our interactions with other life forms. The search for extraterrestrial life continues to be one of the driving forces behind many space missions and astronomical studies. Initiatives like SETI, Search for Extraterrestrial Intelligence, aim to detect signals from advanced civilizations, employing a variety of techniques to scan the cosmos for signs of life. Telescopes are constantly scanning the skies for exoplanets, planets outside our solar system, that might have the right conditions for life. The discovery of potentially habitable exoplanets in the habitable zone of their stars raises the tantalizing prospect that we are not alone. As we explore the cosmos, we are also uncovering new phenomena that challenge our understanding of physics and the universe. The discovery of fast radio bursts, FRBs, mysterious and intense bursts of radio emissions originating from distant galaxies, is just one example. These enigmatic signals remain poorly understood, but they are a testament to the surprises that await us as we delve deeper into the cosmos. In summary, space is not just a vast, empty void. It is a dynamic and evolving tapestry of matter, energy, and phenomena that stretches our understanding of the universe. From the birth and death of stars to the mysteries of dark matter and dark energy, the cosmos presents us with endless questions and mind-bending possibilities. The search for life, the exploration of distant worlds, and the contemplation of our place in the universe drive humanity's quest for knowledge and understanding. As we gaze up at the night sky, we are reminded of the enormity of the universe and the fragility of our existence. Each star we see is a sun, with its own story and potential for life. The vast distances, the complexities of cosmic evolution, and the potential for discovering other forms of life inspire both awe and humility. The future of our exploration holds the promise of new discoveries and revelations that could forever change our understanding of reality. Ultimately, the quest for knowledge about space is not just about understanding the universe. It is also about understanding ourselves. Each discovery brings us closer to answering profound questions about our origins, our destiny, and the nature of existence itself. The journey into the cosmos is a journey of exploration and discovery, one that invites us to ponder the mysteries of life, time, and the universe in which we reside. As we continue to explore the mysteries of the universe, we also reflect on our technological advancements and how they have transformed our understanding of space. The development of telescopes, spacecraft, and robotic explorers has revolutionized our ability to observe and study the cosmos. The Hubble Space Telescope, launched in 1990, has provided us with breathtaking images of distant galaxies, nebulae, and the intricate structures of the universe. Its observations have reshaped our understanding of cosmic evolution, leading to significant discoveries such as the accelerated expansion of the universe and the existence of exoplanets. In recent years, the deployment of space-based observatories like the James Webb Space Telescope, JWST, has opened new frontiers in astronomical research. JWST, launched in late 2021, is designed to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust clouds and study the formation of stars and planetary systems. Its ability to observe the light from the earliest galaxies, formed just a few 100 million years after the Big Bang, promises to shed light on the origins of galaxies, stars, and possibly even life itself. As JWST begins its mission, the potential discoveries could deepen our understanding of the universe's history and the processes that have shaped it. Robotic missions have also played a crucial role in expanding our knowledge of the solar system. The Mars rovers, including Spirit, Opportunity, Curiosity, and Perseverance, have provided valuable insights into the geology and climate of the Red Planet. Curiosity's discoveries of ancient riverbeds and organic molecules indicate that Mars may have once harbored conditions suitable for life. Perseverance is tasked with collecting samples for future return missions, a key step in the ongoing exploration of Mars and the search for past life. Beyond Mars, missions to other celestial bodies have yielded incredible findings. The New Horizons spacecraft's flyby of Pluto in 2015 provided the first detailed images of the dwarf planet, revealing a complex world with mountains, valleys, and even possible subsurface oceans. The Voyager probes, launched in the 1970s, continue to transmit data from interstellar space, providing invaluable information about the outer solar system and the heliosphere, the bubble of solar wind that surrounds our solar system. The search for life has also led to intriguing investigations of moons within our solar system, such as Europa and Enceladus. Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy crust. The potential for this ocean to harbor life makes Europa a compelling target for future exploration. Similarly, Enceladus, a moon of Saturn, has been found to eject plumes of water vapor and organic compounds from its south pole, suggesting that it may also have conditions suitable for life. Upcoming missions, such as NASA's Europa Clipper and the European Space Agency's Jupiter Icy Moons Explorer, JUICE, aim to study these intriguing worlds in greater detail. As we ponder the potential for life beyond Earth, we must also consider the ethical implications of our explorations. The discovery of extraterrestrial life, whether microbial or intelligent, could have profound consequences for our understanding of ourselves and our place in the universe. How should we approach the exploration of other planets and moons that may host life? Moreover, the prospect of sending humans to Mars and beyond raises additional ethical questions. How do we balance our desire to explore and expand our horizons with the responsibility to protect the environments we encounter? The debate around planetary protection emphasizes the need to safeguard both our own biosphere and the potential biospheres of other worlds. As we embark on human missions to Mars and beyond, we must remain vigilant in our commitment to responsible exploration. The study of astrobiology, the field that examines the potential for life in the universe, is crucial to understanding how life might emerge and evolve on other planets. This discipline considers extreme environments on Earth, such as hydrothermal vents, acidic lakes, and frozen tundras, as analogues for potential habitats on other celestial bodies. By studying extremophiles, organisms that thrive in harsh conditions, scientists gain insights into the resilience of life and its ability to adapt. This knowledge informs the search for life in environments once thought to be inhospitable, broadening our perspective on what constitutes a habitable environment. In the search for extraterrestrial intelligence, SETI, scientists are not only listening for signals from advanced civilizations but also exploring the possibility of non-technological life forms. The quest to find biosignatures, chemical indicators of life, in the atmospheres of exoplanets is a focal point of current research. Telescopes like the JWST are equipped to analyze the light spectra of distant exoplanets, searching for signatures of oxygen, methane, and other gases that may suggest the presence of biological processes. The discovery of such biosignatures would revolutionize our understanding of life beyond Earth. The challenge of communication with potential extraterrestrial civilizations is another captivating aspect of the search for life. The vast distances between stars present significant obstacles to instant communication. The time it takes for light to travel between celestial bodies means that any message sent would take years or even centuries to reach its destination. Additionally, the differences in language, culture, and technology could complicate any attempt at meaningful dialogue. Scientists have developed various strategies for encoding messages that could be understood by intelligent beings, such as mathematical concepts or universal scientific principles, but the effectiveness of these approaches remains uncertain. As we continue to explore the cosmos, we must acknowledge that our understanding of space is constantly evolving. Each new discovery challenges our preconceived notions and compels us to rethink our place in the universe. The interplay between science and philosophy becomes evident as we grapple with the existential questions that arise from our exploration. The very act of looking up at the stars inspires awe and wonder, igniting a sense of curiosity that drives us to seek knowledge beyond our own planet. The pursuit of knowledge about space is not merely a scientific endeavor, it is also a deeply human one. The drive to explore the unknown reflects our intrinsic desire to understand ourselves, our origins, and our future. As we gaze into the cosmos, we are reminded that we are a small part of a vast and intricate universe, filled with wonders waiting to be discovered. The exploration of space offers us not only the promise of new knowledge, but also the opportunity to unite as a species in a common goal. As we face global challenges on Earth, such as climate change, resource depletion, and social inequality, our efforts to explore and understand the universe can serve as a reminder of our shared humanity. The quest for knowledge and the search for life beyond our planet have the potential to inspire cooperation, collaboration, and a sense of belonging to a greater cosmic community. In conclusion, the mind-blowing facts about space remind us of the profound mysteries that lie beyond our home planet. From the vast distances between stars to the possibilities of extraterrestrial life, our exploration of the cosmos is a testament to human curiosity and ingenuity. As we continue to push the boundaries of knowledge, we are not only seeking answers to fundamental questions but also embarking on a journey that deepens our connection to the universe and to each other. The night sky beckons us to explore, to dream, and to discover, as we endeavor to unlock the secrets of the cosmos and our place within it. The ongoing exploration of space has prompted humanity to reconsider its very definition of life and consciousness. As we probe the depths of the cosmos and gather evidence of potential life-sustaining environments, we find ourselves redefining the parameters that characterize life. The search for extraterrestrial life is not limited to just finding intelligent civilizations. It encompasses a broader quest to understand the diversity of life forms and the various conditions under which they can thrive. Astrobiology stands at the intersection of biology and astronomy, focusing on the potential for life in the universe. Scientists studying extremophiles, organisms that can survive in extreme conditions on Earth, have begun to understand that life can exist in forms and environments previously thought to be uninhabitable. These discoveries encourage us to expand our search for life beyond the familiar confines of Earth. For instance, the presence of microbial life in the subsurface oceans of Europa or the geysers of Enceladus exemplifies how life might endure in hostile environments. One of the most significant milestones in our quest to understand extraterrestrial life occurred with the discovery of thousands of exoplanets in recent years. Using methods such as the transit method and radial velocity, astronomers have identified planets orbiting distant stars, many of which lie within the habitable zone, the region where conditions might be just right for liquid water to exist. This has broadened our perspective on the potential for life elsewhere in the universe. The sheer diversity of these exoplanets, ranging from gas giants to rocky worlds, underscores the complexity of planetary systems and the myriad possibilities for life beyond our solar system. The concept of the Goldilocks zone, or habitable zone, has become a focal point in the search for exoplanets. This is the region around a star where temperatures are suitable for liquid water, a critical ingredient for life as we know it. However, scientists are now beginning to realize that the potential for life may not be limited to planets within this zone. For example, some moons, like Europa and Titan, are believed to have subsurface oceans, providing environments where life could exist despite their distance from their respective stars. As we study these celestial bodies, the importance of understanding planetary atmospheres cannot be overstated. An atmosphere plays a vital role in regulating temperature and protecting life from harmful radiation. The detection of gases such as oxygen, methane, and carbon dioxide in the atmospheres of exoplanets can serve as biosignatures, indicating potential biological processes. The ability to analyze these atmospheres is a significant step toward uncovering the existence of life beyond Earth. In addition to the scientific aspects of our search for life, the cultural and philosophical implications are profound. The discovery of extraterrestrial life, particularly intelligent life, could reshape our understanding of existence, morality, and our place in the universe. It raises questions about the uniqueness of human civilization and the potential for communication and collaboration with other sentient beings. The implications extend beyond science, influencing art, literature, and even our collective psyche. As we ponder these existential questions, the concept of the Fermi paradox emerges as a significant topic of discussion. This paradox highlights the apparent contradiction between the vast number of stars and potentially habitable planets in the universe, and the lack of evidence for extraterrestrial civilizations. If the universe is teeming with life, where is everyone? Several hypotheses have been proposed to address this paradox, ranging from the idea that advanced civilizations self-destruct to the possibility that they are avoiding contact with us. This paradox invites us to consider the fragility of intelligent life and the challenges of technological advancement. Moreover, the philosophical implications of discovering extraterrestrial life prompt us to reevaluate our notions of consciousness and intelligence. If life exists in forms vastly different from our own, how do we define intelligence? The potential for diverse forms of consciousness challenges our understanding of sentience and raises ethical considerations regarding how we should treat non-human intelligences. These discussions encourage us to think critically about our responsibilities as stewards of life, both on Earth and beyond. As we delve deeper into the cosmos, we encounter the concept of the multiverse, suggesting that our universe may be just one of many. This idea, while still speculative, posits that other universes may exist with different physical laws and conditions, potentially hosting entirely different forms of life. The multiverse theory invites us to imagine the infinite possibilities of existence, and raises questions about the nature of reality itself. It challenges our understanding of space and time and encourages us to expand our horizons beyond the observable universe. In contemplating the vastness of space, we are reminded of the profound interconnectedness of all things. The elements that compose our bodies, carbon, hydrogen, oxygen, and nitrogen, were forged in the hearts of stars. The cosmic processes that shaped our universe are intricately linked to our existence. As we gaze at the stars, we recognize that we are a part of this grand tapestry, connected to the universe in ways we have yet to fully understand. The concept of cosmic perspective is fundamental to our exploration of space. This perspective encourages us to appreciate the beauty and complexity of the universe while fostering a sense of humility about our place within it. As we expand our understanding of the cosmos, we also deepen our appreciation for the fragility of life on Earth. The challenges we face, climate change, resource depletion, and social inequality, are reminders of the importance of stewardship and cooperation. The pursuit of knowledge about space can inspire us to work together as a global community, united in our quest to protect our planet and seek answers to the fundamental questions of existence. As technology continues to advance, the prospect of human colonization of other planets becomes increasingly plausible. Companies like SpaceX are actively working on developing the technologies necessary to transport humans to Mars, with ambitious plans for establishing a sustainable presence on the Red Planet. The potential for humanity to become a multiplanetary species raises important questions about our responsibilities and the ethical considerations involved in terraforming other worlds. As we venture into the cosmos, we must ensure that our explorations are conducted responsibly, preserving the integrity of the celestial environments we encounter. The desire to explore space and understand the universe is rooted in our innate curiosity and sense of wonder. The night sky has captivated humanity for millennia, inspiring mythologies, philosophies, and scientific inquiries. As we uncover the mysteries of the cosmos, we not only satisfy our curiosity but also fuel our imagination. The wonders of space, whether they be the swirling colors of a nebula, the dance of distant galaxies, or the possibility of life beyond our planet, serve as reminders of the beauty and complexity of existence. As we continue to gather knowledge about the universe, we also engage in a deeper dialogue about our role within it. The exploration of space invites us to confront our shared humanity and consider how our actions impact not only our planet but also the potential for life elsewhere. The ethical considerations surrounding space exploration and the search for extraterrestrial life remind us of the importance of stewardship, responsibility, and respect for all forms of existence. In conclusion, the mind-blowing facts about space invite us to reflect on the profound mysteries that surround us. From the vastness of the cosmos to the potential for extraterrestrial life, our exploration of space is a testament to the resilience of human curiosity and the pursuit of knowledge. As we continue to push the boundaries of our understanding, we are reminded of the interconnectedness of all things and the importance of approaching our explorations with humility and respect. The cosmos beckons us to explore, to dream, and to discover, and in doing so, we embark on a journey that unites us as a species and deepens our appreciation for the wonders of existence. As we expand our understanding of space, we also grapple with the implications of our discoveries for humanity's future. The technological advancements that arise from our explorations not only enhance our ability to navigate the cosmos but also influence various aspects of our daily lives on Earth. Innovations stemming from space research have led to developments in telecommunications, medicine, and environmental monitoring, demonstrating that our quest to understand the universe often yields practical benefits for society. For instance, satellite technology has revolutionized how we communicate and monitor climate change. Earth observation satellites provide critical data that helps scientists study weather patterns, track natural disasters, and assess the health of ecosystems. This information is invaluable for disaster response and resource management, illustrating how space exploration can directly impact our ability to address pressing global challenges. Moreover, space exploration has a unique ability to inspire and unite people across cultural and national boundaries. The awe-inspiring images captured by telescopes like the Hubble Space Telescope and missions such as the Mars rover have transcended political and geographical divides, inviting a collective appreciation for the beauty and mystery of the universe. The sight of distant galaxies, nebulae, and the rugged terrain of alien worlds captivates the imagination and ignites curiosity in people of all ages. In education, space exploration serves as a powerful tool for fostering scientific literacy and inspiring the next generation of innovators and explorers. Programs designed to engage students with hands-on activities related to space science, robotics, and astronomy encourage critical thinking and problem-solving skills. By sparking interest in STEM, science, technology, engineering, and mathematics fields, we ensure a continuous flow of talent and creativity that is vital for future discoveries and advancements. The interplay between space exploration and art is also noteworthy. Artists have long drawn inspiration from the cosmos, creating works that reflect humanity's relationship with the universe. From literature to visual arts, the themes of space, exploration, and the unknown resonate deeply with our collective psyche. This fusion of science and art encourages a holistic understanding of the universe and highlights the myriad ways in which we can interpret and connect with our surroundings. As we continue to search for extraterrestrial life, the ethical considerations surrounding our encounters become increasingly complex. The idea of contacting alien civilizations raises profound questions about the implications for both humanity and the beings we might encounter. How would we communicate with them? What responsibilities would we bear in terms of protecting their existence and respecting their autonomy? These questions invite us to consider the broader ethical framework within which our exploration occurs. The potential for discovering intelligent extraterrestrial life could lead to a reevaluation of human values and societal norms. The realization that we are not alone in the universe could foster a sense of humility, prompting us to reflect on our own behavior as a species. It may encourage greater cooperation among nations, as we recognize our shared responsibility for safeguarding our planet and seeking peaceful interactions with other forms of consciousness. While we engage in this exploration, we must also confront the challenges posed by our own advancements. The pursuit of technology and space exploration has, at times, come with consequences for the environment. The proliferation of space debris, the potential for asteroid mining, and the ethical implications of terraforming other planets are pressing issues that require thoughtful consideration. As we venture into space, we must ensure that our actions reflect a commitment to sustainability and responsible stewardship, both on Earth and beyond. The concept of planetary protection plays a vital role in our explorations. The contamination of celestial bodies with Earth microbes could jeopardize the integrity of scientific investigations and potentially harm indigenous life forms. Conversely, the introduction of extraterrestrial organisms to our biosphere could pose significant risks. As we prepare for missions to other planets, protocols for planetary protection are essential to ensure that we do not inadvertently disrupt existing ecosystems. The importance of international cooperation in space exploration cannot be overstated. Collaborative efforts, such as the International Space Station, ISS, demonstrate how nations can come together to achieve common goals. The ISS serves as a microcosm of cooperation, fostering scientific research and technological advancements, while promoting peaceful relations among countries. The challenges of space exploration transcend national boundaries, emphasizing the need for a unified approach to address issues such as resource allocation, space traffic management, and environmental protection. As we look to the future, the idea of a sustainable human presence beyond Earth becomes increasingly tangible. The development of space habitats and life support systems is critical for long-duration missions, whether to the Moon, Mars, or beyond. Research on how to grow food in space, recycle waste, and generate energy will be essential for establishing colonies that can thrive independently. This endeavor not only has implications for potential colonization but also serves as a testing ground for sustainable practices that can be applied to address challenges on Earth. The allure of space travel has captured the imagination of individuals and organizations alike, leading to the rise of commercial space ventures. Companies like SpaceX, Blue Origin, and Virgin Galactic are pioneering efforts to make space travel accessible to private citizens. While this commercialization of space presents exciting opportunities, it also raises questions about equity and accessibility. Ensuring that space exploration benefits all of humanity rather than just a privileged few is a challenge that must be addressed as we move forward. The quest for knowledge about the universe is a profoundly human endeavor, driven by our innate curiosity and desire to explore the unknown. The journey of discovery has the power to unite us as a species, fostering a sense of shared purpose and interconnectedness. As we uncover the mysteries of space, we are reminded of our collective responsibility to protect our planet and seek answers to the fundamental questions that define our existence. The mysteries of dark matter and dark energy further underscore the complexity of the universe. Although they make up approximately 95% of the universe's total mass energy content, little is understood about their true nature. Dark matter, which does not emit light or energy, influences the gravitational pull of galaxies, while dark energy is thought to drive the universe's accelerated expansion. The quest to unravel the secrets of these enigmatic components could fundamentally reshape our understanding of physics and the cosmos. In addition to the mysteries of dark matter and dark energy, the concept of black holes remains one of the most captivating and perplexing topics in astrophysics. These regions of spacetime exhibit such strong gravitational forces that nothing, not even light, can escape from them. The formation of black holes occurs when massive stars undergo gravitational collapse, leading to the creation of singularities, points of infinite density. The study of black holes challenges our understanding of gravity, time, and the fabric of the universe itself. Recent advancements in technology have allowed scientists to capture images of black holes, including the groundbreaking Event Horizon Telescope image of the supermassive black hole at the center of the galaxy M87. This achievement not only confirms the existence of black holes but also provides a glimpse into their fascinating dynamics. The study of black holes raises profound questions about the nature of reality and the limits of our understanding of the universe. As we explore the cosmos, we are also reminded of the potential for cosmic disasters. The possibility of asteroid impacts, gamma-ray bursts, and supernovae events serve as a reminder of the dynamic and sometimes violent nature of the universe. While these events are rare on human timescales, they highlight the importance of monitoring and understanding potential threats to our planet. Efforts to develop early warning systems for asteroid detection, for example, are crucial for safeguarding Earth from catastrophic events. The universe, in its vastness and complexity, inspires wonder and curiosity that knows no bounds. From the intricate dance of galaxies to the potential for life on distant worlds, every aspect of the cosmos invites exploration and discovery. As we delve deeper into the mysteries of space, we recognize that we are part of a grand narrative that transcends time and space, woven together by the threads of existence itself. In conclusion, the mind-blowing facts about space reveal the beauty, complexity, and interconnectedness of the universe. As we continue our exploration, we are reminded of the importance of curiosity, collaboration, and ethical responsibility. The quest for knowledge about the cosmos is not just about uncovering scientific truths, It is also a journey that shapes our understanding of ourselves and our place within the universe. The wonders of space invite us to dream, to question, and to explore, igniting the spark of curiosity that lies at the heart of the human experience. As we progress further into the vastness of space, we encounter phenomena that challenge our perceptions of reality and stretch the limits of human understanding. One such phenomenon is the existence of quasars, supermassive black holes at the centers of distant galaxies that are actively consuming matter. As this matter spirals into the black hole, it emits tremendous amounts of energy, outshining entire galaxies and making quasars some of the brightest objects in the universe. These luminous beacons provide valuable insights into the early universe and the formation of galaxies, shedding light on cosmic evolution over billions of years. Quasars not only reveal the presence of black holes but also serve as a tool for measuring vast cosmic distances. By studying the light emitted by quasars, astronomers can ascertain how far away these objects are, offering a glimpse into the universe's expansion. The study of quasars thus allows us to probe the structure and history of the cosmos, contributing to our understanding of fundamental questions about the nature of space and time. Another captivating aspect of space is the potential for exoplanets, planets that orbit stars outside our solar system. The discovery of thousands of exoplanets has revolutionized our understanding of planetary systems, revealing a staggering diversity of worlds that challenge traditional models of planetary formation. Some exoplanets exist in the habitable zone, where conditions may be right for liquid water and potentially life. The search for extraterrestrial life has shifted from theoretical musings to scientific inquiry, with missions like the Kepler Space Telescope and the Transiting Exoplanets Survey Satellite, TESS, playing pivotal roles in identifying potentially habitable exoplanets. The implications of discovering life beyond Earth are profound. The mere existence of microbial life on another planet could reshape our understanding of biology, evolution, and the conditions necessary for life. It raises philosophical questions about humanity's place in the universe and the possibility of shared existence with other sentient beings. These inquiries not only ignite curiosity but also inspire scientific investigations aimed at answering the age-old question, are we alone in the universe? As we venture deeper into the cosmos, the concept of time itself takes on new meanings. In the realms of black holes and relativistic physics, time behaves differently than our everyday experiences suggest. For instance, the intense gravitational pull of a black hole warps spacetime, causing time to slow down significantly for an observer approaching the event horizon. This phenomenon, known as gravitational time dilation, highlights the intricacies of time and its relationship with gravity, as described by Einstein's theory of general relativity. Moreover, the expansion of the universe poses questions about the nature of time itself. As galaxies move away from each other due to the expansion of space, it leads to the phenomenon of redshift, where light from distant galaxies shifts toward the red end of the spectrum. This observation is not only a testament to the universe's dynamic nature but also a crucial piece of evidence supporting the Big Bang theory, which posits that the universe has been expanding since its inception. The implications of this expansion raise philosophical questions about the beginning and end of the universe, leading to theories about its ultimate fate. One of the most mind-bending concepts in cosmology is the idea of the multiverse, the hypothesis that our universe is just one of many universes that exist simultaneously. While still speculative, the multiverse theory arises from interpretations of quantum mechanics and inflationary cosmology. It suggests that there could be infinite variations of universes, each with its own set of physical laws, constants, and histories. The implications of a multiverse challenge our understanding of reality, suggesting that our universe may be just one among countless others, each offering unique possibilities for existence. In the search for understanding the cosmos, we also confront the enigmatic nature of dark energy. This mysterious force, which is believed to drive the accelerated expansion of the universe, accounts for approximately 68% of the universe's total energy density. Despite its significant influence on cosmic evolution, dark energy remains one of the most elusive components of the universe, with little known about its true nature. Researchers are actively investigating various theories, including the possibility that dark energy is a property of space itself or a manifestation of a yet-to-be-discovered field. Additionally, the phenomenon of gravitational waves, ripples in spacetime caused by cataclysmic events such as merging black holes or neutron stars, has opened up a new window for observing the universe. Detected for the first time in 2015 by the LIGO Observatory, gravitational waves offer a novel way to study cosmic events that are often invisible to traditional telescopes. This groundbreaking discovery has not only confirmed a key prediction of general relativity, but has also paved the way for a new era of astrophysics, where the universe can be explored through both light and gravitational waves. The beauty of the cosmos is not limited to its grand phenomena. It also extends to the intricate structures that populate the universe. Galaxies, the building blocks of the cosmos, come in various shapes and sizes, each telling a unique story of formation and evolution. The Hubble classification scheme categorizes galaxies into spirals, ellipticals, and irregulars, revealing the diversity of stellar populations and cosmic dynamics. The interactions between galaxies, including mergers and tidal forces, play a significant role in shaping their morphology and influencing the distribution of matter in the universe. Our own galaxy, the Milky Way, is a barred spiral galaxy containing billions of stars, many of which are accompanied by planetary systems. The structure of the Milky Way consists of a central bulge, a flat disk with spiral arms, and a surrounding halo of dark matter. As we explore our galactic neighborhood, we uncover the history of stellar formation, supernova explosions, and the interplay between gravity and dark matter that governs the motion of stars and galaxies. The study of cosmic microwave background radiation, CMB, provides further insight into the early universe. This faint afterglow of the Big Bang fills the cosmos and carries information about the universe's infancy, approximately 380,000 years after its creation. Analyzing the CMB has yielded remarkable discoveries about the universe's age, composition, and the seeds of structure that led to the formation of galaxies and clusters. This radiation serves as a cosmic snapshot, offering a glimpse into the conditions that shaped the universe's evolution. Exploring the possibility of time travel, a concept often relegated to the realm of science fiction, invites fascinating discussions about the nature of causality and the fabric of spacetime. While traversable wormholes and other theoretical constructs exist within the framework of general relativity, the practical challenges of time travel remain insurmountable with our current understanding of physics. Yet, the mere contemplation of such possibilities opens avenues for creative thought and exploration of the fundamental nature of reality. As we reflect on the vastness of space and the myriad wonders it holds, we recognize the interconnectedness of science, philosophy, and the human experience. Our pursuit of knowledge about the cosmos is not merely an intellectual endeavor. It is a journey that shapes our identity and influences our understanding of existence itself. The quest to unravel the mysteries of space inspires awe and curiosity, igniting a sense of wonder that transcends generations and cultures. In summary, the mind-blowing facts about space offer a glimpse into the incredible complexity and beauty of the universe. From the phenomena of black holes and quasars to the search for exoplanets and the exploration of dark energy, each discovery contributes to a larger tapestry of knowledge that defines our understanding of reality. The interplay of science, philosophy, and art enriches our perspective on the cosmos, fostering a deep appreciation for the mysteries that lie beyond our planet. As we continue to explore the universe, we embark on a journey of discovery that shapes our understanding of ourselves and our place in the grand narrative of existence. As we delve deeper into the cosmos, we encounter more astonishing facts that expand our understanding of space and challenge our perceptions of reality. One of the most captivating phenomena in the universe is the existence of neutron stars. These remnants of supernova explosions are incredibly dense, packing the mass of the Sun into a sphere only about 20 kilometers in diameter. A sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth, showcasing the extreme conditions that govern their existence. Neutron stars exhibit fascinating properties, including strong magnetic fields and rapid rotation. Some neutron stars emit beams of radiation from their magnetic poles, resulting in a lighthouse effect as they spin, these are known as pulsars. The precise timing of their pulses provides invaluable insights into the nature of gravity and the behavior of matter under extreme conditions. Studying pulsars has also led to the detection of gravitational waves, further enriching our understanding of the universe's dynamics. Another mind-blowing aspect of space is the concept of black holes, particularly their role in the life cycle of stars. Massive stars, after exhausting their nuclear fuel, undergo gravitational collapse, resulting in the formation of black holes. These cosmic giants have gravitational pulls so strong that not even light can escape them, making them invisible against the backdrop of space. The event horizon defines the boundary of a black hole, beyond which nothing can return. The study of black holes challenges our comprehension of physics, as the laws governing their behavior often contradict our conventional understanding of reality. The existence of supermassive black holes at the centers of galaxies raises intriguing questions about their formation and influence on cosmic evolution. These behemoths can contain billions of times the mass of the Sun and play a crucial role in shaping their host galaxies. The interplay between supermassive black holes and galactic dynamics is an area of active research, as scientists seek to understand how these colossal entities affect star formation and the distribution of matter within galaxies. Moreover, the phenomenon of gravitational lensing provides yet another mind-bending insight into the universe. When light from distant objects passes near a massive object, such as a galaxy or black hole, it bends due to the curvature of spacetime, creating distorted images or multiple images of the background source. This effect not only serves as a powerful tool for studying dark matter and the distribution of mass in the universe, but also allows astronomers to observe objects that would otherwise be too faint or distant to detect. The study of cosmic background radiation further enriches our understanding of the early universe. This radiation is a remnant of the Big Bang, providing a snapshot of the universe just 380,000 years after its formation. By analyzing the fluctuations in the cosmic microwave background, scientists have gleaned information about the universe's composition, structure, and evolution. This ancient light serves as a cosmic relic, offering profound insights into the conditions that led to the formation of galaxies, stars, and ultimately, life. Another intriguing concept in modern astrophysics is the idea of cosmic inflation, a theory suggesting that the universe underwent rapid expansion in the first moments after the Big Bang. This inflationary period explains the uniformity of the cosmic microwave background and the large-scale structure of the universe. It proposes that tiny quantum fluctuations during inflation became the seeds for the galaxies and structures we observe today. The implications of inflation challenge our understanding of time and space, suggesting that our universe may have expanded faster than the speed of light, an idea that defies our conventional understanding of causality. As we explore further, the concept of dark matter emerges as a crucial yet elusive component of the universe. Comprising approximately 27% of the universe's total mass energy content, dark matter does not emit, absorb, or reflect light, making it undetectable by conventional means. Its presence is inferred through gravitational effects on visible matter, such as galaxies and galaxy clusters. The nature of dark matter remains one of the most significant challenges in contemporary astrophysics, with various candidates, including weakly interacting massive particles, WIMPs, and axions, being proposed to explain its existence. The investigation into dark matter is not only about understanding its composition but also about deciphering its role in the evolution of the universe. Dark matter acts as a scaffolding for visible matter, influencing the formation and distribution of galaxies. Without dark matter, the universe as we know it would be vastly different, with galaxies unable to form and evolve as they have. In addition to dark matter, the exploration of dark energy presents another layer of complexity to our understanding of the universe. Dark energy is thought to account for approximately 68% of the universe's total energy density, and is responsible for the observed accelerated expansion of the universe. Its true nature remains a mystery, with theories ranging from a cosmological constant, as suggested by Einstein, to dynamic fields that vary over time and space. Understanding dark energy is vital for unraveling the ultimate fate of the universe, as it influences how galaxies move apart and the overall structure of the cosmos. The search for extraterrestrial life has intensified with the discovery of extremophiles, organisms that thrive in extreme conditions on Earth, such as deep-sea hydrothermal vents and acidic lakes. These findings challenge our assumptions about the habitable zones required for life and suggest that life may exist in environments previously considered inhospitable. The exploration of moons like Europa and Enceladus, which harbor subsurface oceans beneath icy crusts, has sparked interest in astrobiology, raising the possibility of finding life beyond our planet. The advancement of space exploration technologies has enabled missions to Mars, the outer planets, and even interstellar space. The Voyager spacecraft, launched in 1977, continues to transmit data from the far reaches of our solar system, providing valuable insights into the heliosphere and the interstellar medium. The James Webb Space Telescope, set to launch in the near future, promises to revolutionize our understanding of the universe by allowing astronomers to observe distant galaxies, stars, and exoplanets with unprecedented clarity. The concept of time in the universe also prompts fascinating inquiries. Einstein's theory of relativity suggests that time is not a constant. Rather, it is relative and can be affected by factors such as velocity and gravity. The notion of time dilation means that time moves differently for observers in different gravitational fields or moving at different speeds. This realization leads to intriguing paradoxes, such as the twin paradox, where one twin traveling at relativistic speeds ages more slowly than their stationary counterpart. As we contemplate the vastness of space, the scale of the universe becomes evident. The observable universe stretches approximately 93 billion light-years across, containing an estimated 100 billion galaxies, each with billions of stars and potentially countless planets. This mind-boggling expanse raises questions about our significance in the grand scheme of existence. While our planet is but a tiny speck in the cosmic ocean, the search for meaning and connection remains a central theme in human exploration and inquiry. The possibility of encountering extraterrestrial intelligence adds another layer of complexity to our understanding of the universe. The Fermi paradox. If the universe is so vast, where is everybody? Poses a compelling question about the existence of advanced civilizations. Despite the vast number of stars and planets, we have yet to detect definitive signs of extraterrestrial life. This paradox has sparked numerous theories, from the idea that intelligent civilizations are short-lived to the notion that they are intentionally avoiding contact with us. As we ponder these questions, the intersection of science and philosophy emerges. The exploration of space invites us to reflect on our place in the universe, the nature of consciousness, and the interconnectedness of all living things. The pursuit of knowledge about the cosmos is not merely an intellectual endeavor. It is a profound journey of self-discovery that shapes our understanding of existence. In conclusion, the mind-blowing facts about space reveal a cosmos filled with mysteries, challenges, and wonders that continue to inspire human curiosity and exploration. From the extreme conditions of neutron stars and black holes to the enigma of dark matter and dark energy, each discovery enriches our understanding of the universe and our place within it. The quest for knowledge drives us to explore the unknown, unravel the complexities of the cosmos, and ultimately confront the fundamental questions of existence. As we embark on this journey of discovery, we embrace the beauty and intricacies of the universe, fostering a deep appreciation for the interconnectedness of all things in the cosmic tapestry. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.